Today's topic is all about waves. So as we go through this PowerPoint, I'm shooting for about 10 minutes or less. Just have your guided notes with you. Whenever you see any kind of underlined words, that means that you need to write down those underlined words in your guided notes. If you have any questions, write them down on the side or email me, or we can talk about them the next time we get to class, okay? So starting off with waves, trying to define a wave might be difficult, and you probably think of water waves or maybe sound waves, but to actually describe what water waves and sound waves and light waves all have in common, it might be tough. So what is it? A wave is just a disturbance in matter moving from one location to another. And the disturbance that we're talking about, if you look at the picture down below, where would you say the disturbance is? Is it going to be to the left where the water's low, right in the middle where the water's high, or behind it all the way to the right where the water's low again? And I think everybody would agree that the disturbance is actually at the peak of that water wave. So this disturbance, it's a movement of some kind of material, and in the case of the picture, the material is water. But it's a movement of some kind of material from where it would normally be. And where it would normally be is called the resting position. So as you can see, normally water is going to be low. Gravity's going to pull it down, and it's going to find the lowest spot in its container. In this case, it's a big giant swimming pool. So there's the rest position. There's a rest position behind the wave as well. Water in the wave is actually at the highest energy possible. And these waves, they move in predictable ways. And so we can actually discover laws about nature and how these waves move. And that's a little bit of what today's about. We can't forget that it took energy to make the original disturbance or the original disruption of the water. If you've ever been to a wave park, it takes time for them to build up enough energy to produce another wave. So we have that energy. Now, obviously, that wave, as it moves, we know it has energy because if it hits you, it can knock you over. And that wave's energy can be traced back all to the original disturbance. That means that waves, all they do is they carry the disturbance of the original disruption. And it doesn't matter if we're talking about light waves, radio waves, water waves, or sound waves. There's an original disruption that requires energy, and then the wave just transfers that energy over a distance. So waves carry energy of the original disruption. There's a lot of waves that you've heard me talk about already, but the way that we name them is according to what kind of matter. The way that we name them is according to what kind of matter is being disrupted. And I think you need to write in a section here. I forgot to underline it on the PowerPoint, I'm sorry. They're named according to the matter that's being disrupted. For example, a wave of water is just disrupting water. I think that's pretty obvious. We just call them waves. We don't call them water waves because they're so common. Sound waves, you might not know, they actually disrupt air. They'll compress air, which is why in outer space, if there's an explosion, there will be no noise because there's no air to compress in outer space. There's a vacuum. Seismic waves you've heard of in upper grade school and in junior high. You learned about seismic waves when you learned about earthquakes. And seismic waves are a disruption of the Earth's crust, and they can all be traced back to these tectonic plates that hit each other and will either go above or below. And that creates a lot of energy that's then transferred through the Earth's crust. The last kind of wave that we're going to be dealing with are electromagnetic waves. Sometimes we call these light waves. And here's where it gets a little crazy and a little bit science fiction. It almost might sound like Star Wars, but it's real, and that's kind of why it's crazy, because it's a disruption in the electrical and magnetic forces. Normally, in the air right around us, those forces are usually balanced or pretty close to balanced. And if the forces are balanced, there's not going to be any kind of movement. Well, if there's an unbalance in the force, like if my two fingers push differently, my hand will actually move if there's an unbalance in force. And so if all an electromagnetic wave is an unbalance in the electrical forces and in the magnetic forces in a very small area. And those can actually move across space. And we call that light. It's crazy. Right now, you're working off of Wi-Fi, watching this video, and so you're actually benefiting from electromagnetic waves communicating from the Wi-Fi hotspot to your computer. Trust me, it happens. It's crazy, but it happens. Now, all of these waves, whether we're talking about water, sound, seismic, or electromagnetic, they all fit into two camps. Let me quick play this video to show the two types of waves.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves.
So if we stop right there, did you notice how the force that began this disturbance pushed that way, and then the wave also went that way? So if they're going in the same direction, call it longitudinal waves. Sometimes they're called compression waves.
In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
So this hand, you yank the spring up, so the disturbance was going up and down, but the wave is still moving from left to right. So we call this a transverse wave because the disturbance is perpendicular to the movement of energy. Let me pause that. All right, stuff to write down here. Everything to write down, I'm sorry. So all waves that we're going to be dealing with, they can either fall into two camps, and it depends on how they disrupt the medium that they carry the energy. If they disrupt it the first way that we talked about, whereas they disrupt it in the same direction as the energy being traveled, we call them longitudinal waves. If the disruption is perpendicular, up and down to the way that the movement of energy is traveling, we call them transverse waves. A little bit more on that. During the longitudinal waves, we already said that the disturbance moves particles in the same direction that the energy is moving. There's a picture of it right there. Longitudinal waves. Some examples. We got sound waves, and they will actually move particles of air. Take a look at this picture and just study it really close. We would be having a speaker here that would be vibrating, and right now it is vibrating a pulse every boom. Boom, boom. Watch that red line. Boom, boom. And so it's compressing these air particles, and this compression wave moves throughout the medium of air. And that's why we call them a compression wave, because if we could measure the air pressure, it would be higher where there'd be more dots, basically. And that's how sound works. Those are longitudinal waves. The other type of wave that we said was a transverse wave. And here the disturbance moves up and down, perpendicular to the energy's direction. So some examples of transverse waves, the two types that you're going to be familiar with are normal water waves. And water waves, they are important to understand how water waves works because, listen, the worst natural disaster in the history of mankind that we know of happened in 2004 where a tsunami, a water wave, killed 200-some thousand people on Christmas Day. So very important that we know about how water waves work. Also seismic waves. It's important that we know how seismic waves work because they're responsible for earthquakes. Also electromagnetic waves will behave in this pattern, but here's the crazy thing. They don't move particles. And because electromagnetic waves don't move particles, they don't need matter to travel through. That's why light can travel through space, but sound cannot. Sound must move air molecules. Electromagnetic waves just disrupt the force. Parts of a wave that you need to know, just so we can communicate a little bit better, are right here. The first part of a wave, and these are transverse waves if you didn't get this yet. The first is the wavelength, and the wavelength is from peak to peak. Okay, now that peak has a... Alright, looks like I messed this up. I'll just go through them here. Pause for a second so you can put all of these in your diagram. But let's start off with the crest. Find the crest and find the trough. Alright, the crest and the trough are the 2 points at which the matter is at its highest energy state. The reason why it's at its highest energy state is because it is farthest from the rest position. The rest position is where matter would normally be at if it's not being disrupted. But along comes a disruption and it makes it go away from that rest position. So crest and trough, same thing, just opposite directions. The amplitude is the distance from the rest position. So how high up is the crest or how deep is the trough? We call that amplitude. The distance between crests or the distance between troughs is called the wavelength. So again, some terms that you need to know of: wavelength, rest position, trough, crest, and amplitude. Now the reason why you need to do that and why you need to know these is because we're going to be doing a lot of experiments on waves and the properties of waves, and we're going to be able to have to use these terms quite a bit throughout this course. Alright, so if you have any questions, let me know. You will be having a worksheet that will be going along with these notes, so good luck on that. Refer back to this video if you need any help. Thank you. Bye-bye.